Welcome back to my channel Biochem Bio World. In today's vlog, I'll be discussing SDS-PAGE, that is sodium dodecyl sulfate polyacrylamide gel electrophoresis, which is a very common technique which is used to resolve protein mixtures as well as for the determination of the molecular weight of a particular protein. Okay. So electrophoretic separation of proteins is most commonly performed in PAGE. Okay, and the movement of proteins in polyacrylamide gel electrophoresis depends upon three factors: the charge density of that particular protein, what is the size of it, okay, and what is the shape. Is it globular? Is it fibrous? Okay, so if two proteins, they have the same size, okay, and same shape, they are globular, the one with the greater charge density will move faster. Okay, if two proteins with same charge density, if they are two proteins, they are having the same charge density and they are having the same shape, the smaller protein will move faster. Okay, in comparison to the fibrous proteins, globular proteins move faster. Okay, and because of the fibrous protein, usually what happens, it faces a very, we can say, a frequent frictional force when it moves. Globular proteins, they move faster in comparison to that of fibrous because of the occupation of the smaller space by them. Protein molecules are treated with sodium dodecyl sulfate. Before resolution of a particular protein mixture, as the name suggests, SDS polyacrylamide gel electrophoresis, the proteins, they are treated with this particular anionic detergent. It is a negatively charged anionic detergent which is also termed as sodium lauryl sulfate. I have given the structure in this slide as well. What happens when the protein mixture is treated with sodium dodecyl sulfate? It imparts a large negative charge. It is a negatively charged anionic detergent, and as a result of which there is a negative charge on the protein. It masks the native charge of that protein and giving it a negatively charged. So as a result of this negative charge, these protein molecules, they move towards the positively charged electrode. Okay, proteins treated with SDS have similar charge to mass ratio because approximately 1.5 gram of SDS binds per gram of the protein. Okay, they impart a similar charge to mass ratio. The amount of SDS bounds depend upon the size of the protein. The larger the protein, more is the SDS bound. Okay, the SDS bound polypeptides are flexible rod shaped with uniform negative charge per unit length. Like charges repel each other, the whole protein will having a net negative, will be having negative charges, as a result of which what it happens, it denaturates, it loses its native conformation, it loses its biological activity, and as a result of which it is an extended form of protein. Okay, the resolution of proteins in SDS-PAGE is based upon the molecular weight of the proteins. So the separation of that particular mixture which is treated with sodium dodecyl sulfate will not depend upon the charge density. It will depend upon the molecular weight. The larger the protein, lesser will be its mobility in the gel. The smaller the protein, the more is the mobility of that in the gel, and more mobility in the gel. Okay, SDS-PAGE is usually done in two conditions: reducing and non-reducing conditions. Non-reducing is simply same. Okay, the proteins are treated with the anionic detergent, and and they're loaded into the gel. Okay, and loaded into the gel and into the discontinuous gel, and resolution takes place. Okay, whereas in reducing environment, what happens? In reducing SDS-PAGE, what happens, what we use a reducing agent, for example is beta mercaptoethanol or diethiothriatol, to break the inter-chain or intra-chain disulfide linkages. Okay, for instance, I have a protein X. Okay, I have a protein X. It is having inter-chain disulfide linkage. First, I treated with beta mercaptoethanol. Okay, as a result of which there is a reduction of the disulfide linkages. Further, these reduced protein is treated with SDS, and as a result of which there is extended form of that protein, and I go for the page. Okay, simple for that. ठीक है, it is to break the remaining, we can say, the disulfide linkages. Okay, SDS already does that. It denatures the protein. It results in the loss of the biological activity of that particular protein, but the disulfide linkages are removed by reducing them with the dithiotol or beta mercaptoethanol. Suppose I have a protein which is having two subunits bound by intra-chain disulfide linkages. I treat it with beta mercaptoethanol, as a result of which I get two separate polypeptides. I treat them with SDS and transform them into an extended form and run the page. If this particular protein, I can say, if a particular protein gives a molecular weight of 100 kilodalton in a native page, okay, 100 kilodalton in a native page, and the same protein when run into a reducing SDS page, it giving a 50 kilodalton band, it means that that protein is made up of two subunits. It is made up of two subunits bound by an intra-chain disulfide linkages, and it is having 50 kilodalton subunits. It is an oligomer of two subunits having 50 kilodalton molecular weight. Okay, so hence we can know the subunits of a particular protein by running them firstly through into the native page and then in the SDS reducing page. Thank you so much for watching my channel. That's all for today's vlog.